Hello there, and welcome to the Sleepy Science Secrets. Tonight, we are going to wander together into one of the most quietly astonishing ideas that human minds have ever touched. Imagine this: everything you see, the soft ceiling above you, the gentle weight of your blanket, the slow rise and fall of your own breathing, all of it, every single thing you call real, might be a kind of shimmering picture. A picture that lives on a surface so distant, so vast, and so impossibly thin that the surface itself is almost nothing at all. And yet, somehow, from that almost nothing, everything blooms. Every star, every ocean, every quiet evening, every you. This is the holographic universe. And tonight, we are going to drift through it together, softly, slowly, the way light drifts through still water. Let yourself settle a little more deeply into wherever you are right now. Feel the support beneath you, the mattress, the cushion, the floor, whatever holds you. Let it hold you completely. You do not need to hold yourself up tonight. The world will do that for you. Now, very gently, let your mind reach upward, past the ceiling, past the clouds, past the thin blue skin of the sky, and into the vast breathing darkness of space. It is out there, always, patient, immense, quiet in a way that is deeper than any quiet you have ever known. Scientists who spend their lives thinking about space and time and the very nature of reality have been sitting with a strange and beautiful question for several decades now. The question is this: what if the universe is not quite what it looks like? What if what we experience as three-dimensional space, with its depth and height and width, with things moving through it and time unfolding inside it, is actually a kind of projection, like the image from an old film projector, brilliant and moving and seeming to have depth, but ultimately casting itself out from a flat ribbon of light running through a small, warm machine. This idea has a name. It is called the holographic principle, and tonight we are going to let it unfold around us the way a dream unfolds, gently and without hurry. You might have seen a hologram before, maybe on a credit card or in a science museum. You hold it up and tilt it, and light plays inside it, and somehow, impossibly, a three-dimensional image floats there within the flat surface. Turn it one way, and you see one angle. Turn it another way, and the object seems to rotate. The whole shape is somehow encoded in the flat material, released by light into the appearance of depth and dimension. The holographic principle says something like this about the universe itself: the deep information that makes up everything, every particle, every field, every force, may be encoded not in the volume of space, but on a surface, a boundary, as if the universe is a kind of hologram and we are living inside the projection. This is not a metaphor meant to comfort or confuse. It comes from mathematics, from physics, from the long and careful work of people who spend their nights the way you might spend them, looking up at the stars, wondering what it all means. Let your breath slow now. There is nothing to figure out tonight. Just let the ideas wash over you the way warm water washes over stones. The holographic principle did not arrive all at once. Like most beautiful ideas, it crept in gradually, at first almost unnoticed. The way the light changes in a room before you realize the sun has shifted. It began with a problem, a puzzle about black holes of all things. And the man who first held that puzzle up to the light was a physicist named Jacob Bekenstein. Bekenstein was young when he started thinking about black holes in a new way. A black hole is a place in space where gravity is so strong that nothing, not light, not sound, not anything, can escape once it crosses a certain boundary. That boundary is called the event horizon. Beyond it, the laws of physics as we understand them become very strange indeed. What Bekenstein noticed was something about entropy, which is a word for disorder, for the number of possible arrangements that a thing could have. He realized that the entropy of a black hole was not related to its volume the way you might expect. It was not about how big the black hole was inside. It was related to the area of its event horizon, that surface, that boundary. Let that land softly. The information inside a black hole, all the complexity of everything that has ever fallen in, is described not by the inside, but by the surface. This was the first whisper of the holographic idea. If you enjoy these quiet wanderings, you might like to leave a small comment below. It means the world to us here, and it helps other tired minds find their way to this channel. We are very glad you are here. Stephen Hawking, whose mind was one of the most extraordinary the world has seen, was at first skeptical of Bekenstein's idea. But then Hawking made a discovery of his own that changed everything. He found, using a combination of quantum mechanics and general relativity, two of the great theories of physics, that black holes are not entirely black. They glow very faintly. They release a slow, cold breath of radiation over enormous stretches of time. This radiation is now called Hawking radiation. The existence of this radiation created a new puzzle. If a black hole slowly evaporates, releasing this faint glow and shrinking over trillions of years until it is completely gone, what happens to all the information that fell in? Is it destroyed? Physics says information cannot simply be destroyed. It has to go somewhere. This puzzle is called the information paradox, and it has haunted physicists for decades. But here is what is gentle about this paradox. It is a puzzle that opened a door. Because in trying to understand where the information goes, physicists began to take seriously the idea that information might live on the surface of things, not inside them. Let yourself breathe. Feel the slow rhythm of it. In and out, in and out. The holographic principle was named and formalized by a physicist named Gerard 't Hooft, and then developed further by Leonard Susskind. Susskind in particular was deeply moved by the debate between Hawking and another physicist named John Preskill about whether information was truly destroyed in black holes. Susskind believed it was not, and in working through that belief, he helped build the foundation of what we now call holography in physics. Susskind once said that the universe is not what it looks like. That statement is not alarming when you hear it in a quiet room at night. It is, instead, rather freeing. Because if the universe is more than what it looks like, if there is more going on beneath and behind and around the surface of things, then perhaps there is more to everything than what appears. More to a rainy afternoon, more to a kind word, more to the light coming through a window, more even to this soft darkness you are resting in now. The holographic principle says that all the information needed to describe everything inside a region of space can be encoded on the boundary of that region. Think of it like this. Imagine a very large, very beautiful snow globe. Everything inside it, the tiny village, the falling snow, the little church with its warm light, can in principle be completely described by information written on the glass surface of the globe. You would not need to go inside. The surface would tell you everything. Our universe might be like that snow globe. Except the snow is galaxies, and the glass is something far more abstract and beautiful, a surface at the edge of space itself. Let your body be heavy now. Let your shoulders drop. Let your jaw soften. There is a particular kind of release that comes late at night, when the world outside has finally quieted and you feel yourself beginning to let go of the day. Let that feeling come. We left off with the image of a snow globe, everything inside described by its surface. Let us go a little deeper into that idea tonight, as gently as you like. In 1997, a physicist named Juan Maldacena published a paper that changed the landscape of theoretical physics. It is considered one of the most cited papers in the history of the field, and what it described was something called the ADS/CFT correspondence. Those letters stand for anti-de Sitter space and conformal field theory. Do not worry about the words. What matters is the feeling of what they mean. Maldacena showed, through mathematics of extraordinary elegance, that a certain kind of universe with gravity in it is equivalent to a different kind of universe without gravity on its boundary. The two descriptions are completely equivalent. Every event in the three-dimensional space with gravity corresponds exactly to something happening on the two-dimensional boundary without gravity. And vice versa. This is called a duality. Two different descriptions of the same thing, like two different languages describing the same poem. The poem does not change. Only the language does. Imagine you are watching ripples on a pond. From above, you see the ripples spread, two-dimensional circles moving outward across the surface. But those ripples are also being caused by something happening in three dimensions. A stone dropped, water displaced, pressure waves moving through depth. The surface ripples and the three-dimensional event are two descriptions of the same reality. Maldacena's work suggests that gravity and the three-dimensional universe might be the ripples on a pond, and that the pond's surface tells the full story. Feel how quiet that is. A pond at night, smooth after the ripples have passed. The stars reflected in it, doubled, the real ones above, and their soft ghosts below. The year Maldacena published his paper, he was only 28 years old. He was born in Buenos Aires and grew up with a love of mathematics that found its home in the deep structure of space and time. His paper was circulated informally before it was even formally published, and the response from physicists around the world was immediate and profound. People recognized something true in it, the way you sometimes recognize a piece of music you have never heard before. One of the things that makes Maldacena's work so remarkable is what it says about gravity. Gravity is the force that holds you to the earth, that keeps the moon in its slow arc, that draws galaxies together over billions of years. It is one of the most familiar forces in the universe. And yet, gravity is also the one force that physicists have had the most difficulty reconciling with quantum mechanics, the theory that describes the very small. But in Maldacena's framework, gravity in the bulk of space, in the full three-dimensional interior, emerges from quantum interactions on the boundary. Gravity is not fundamental in this picture. It is a consequence, It arises the way warmth arises from the movement of particles, or the way a melody arises from individual notes. This is a deeply strange and deeply peaceful idea. Gravity, the thing that holds you to your bed, that keeps the moon circling gently above, might be something that emerges from deeper relationships happening somewhere we cannot directly see. Like how the feeling of warmth on your face emerges from something invisible. The movement of light across millions of miles of space. You might want to save this video to a playlist for later. We have a whole collection of these sleepy science wanderings, and each one is a little world of its own, soft, slow, made for nights just like this one. Let your thoughts drift like leaves on water. You do not need to hold them. Just let them float. The ADS/CFT correspondence works in a very specific kind of universe, one with a particular shape called anti-de Sitter space. This space has a kind of curvature, a shape that bends inward like the inside of a saddle. It is not exactly the shape of our universe. Our universe appears to be flat, or very nearly so. But many physicists believe the principle holds more broadly, that holography is not just a feature of that specific mathematical toy universe, but a deep truth about all universes, including ours. There is something comforting about the idea that what looks like a vast three-dimensional universe might be the projection of something simpler, something written on a surface, not simpler in the sense of lesser, but simpler in the sense of more fundamental. The way a single seed contains, in a sense, the whole tree. The information of the tree is there in the seed. The tree is just the seed unfolded in time. The holographic principle suggests that the universe is unfolded information. Everything we see, every mountain, every raindrop, every sleeping child, is the unfolding of something that was, in some sense, already written, not in a fatalistic way, not in a way that takes away meaning or mystery, but in a way that says there is a profound order beneath the surface of things, a coherence, a pattern that holds. Let that land gently. You do not need to understand it fully. Just let it rest beside you, the way a good thought rests beside you before sleep. String theory, which is one of the main candidates for a theory of everything, provided much of the mathematical scaffolding for Maldacena's work. String theory imagines that the most fundamental things in the universe are not point-like particles, but tiny, vibrating strings of energy. Different vibrations produce different particles, different forces, different properties of matter. It is like a cosmic instrument, the universe playing itself into existence. Within string theory, holography arises quite naturally. The mathematics that describes strings in one space connects beautifully to the mathematics of fields on a lower dimensional boundary. The hologram is built into the theory, the way harmony is built into a well-made chord. Notice how your breathing has settled, how the rhythm of it has become its own small lullaby. In for a count, out for a count, the body doing what it has always known how to do, finding its pace, finding its rest. We are drifting deeper into the holographic universe now, deeper into the idea that information is the most fundamental thing there is, more fundamental than matter, more fundamental than energy, more fundamental even than space and time. There is a phrase that the physicist John Archibald Wheeler loved to say. Wheeler was one of the great physicists of the 20th century. He coined the term black hole. He worked alongside both Niels Bohr and Albert Einstein. and he spent his life at the edge of the deepest questions. The phrase he loved was this: it from bit. Information from binary digits. The idea that the physical world, matter, energy, reality itself, is built from information at its most basic level. Wheeler came to this idea late in his life, after decades of thinking about quantum mechanics and gravity. He became convinced that the universe is, in some profound sense, a participatory phenomenon. That information, the asking of questions, the making of observations, the recording of yes or no, is what calls reality into being. This is not mysticism, it is physics, and it connects beautifully with the holographic principle. Because if reality is made of information, and if that information lives on surfaces rather than in volumes, then the universe is something like a vast self-encoding message. A message written on its own edge, reading itself into existence. Feel how still the air is right now, how the room holds you gently without asking anything of you. You're just here, just breathing, just being, and somehow that is enough. One of the most fascinating aspects of holography in physics is what it says about the experience of space. We feel space as real and deep and three-dimensional. We walk through it. We reach out and touch things at various distances. We have a powerful sense of moving through volume. And yet, the holographic principle suggests that this experience of depth might be emergent. It might arise from relationships among quantum fields on a boundary, rather than being a fundamental feature of reality. Think about how a good piece of music can create the sensation of space. A lone violin seems to come from far away. A choir seems to fill the room. The depth you feel in music does not exist in the room. It is created by the brain from patterns of sound. Your experience of depth is real, but the depth itself is constructed. The holographic principle suggests something similar about the space you inhabit. The depth feels real. It is real in every meaningful sense. But it might be constructed. It might emerge from something more fundamental. The way the experience of space in music emerges from something more fundamental than space itself. If you are finding these ideas soothing, we would love it if you dropped a like on the video. It takes only a moment, and it helps us bring these quiet wanderings to more people who need them. There is a researcher named Mark von Ramsdonk whose work helps us feel this idea more vividly. In 2010, he wrote a paper with the gentle title, "Building Up Space-Time with Quantum Entanglement." In it, he argued that the fabric of space, the connective tissue of the universe, is built out of quantum entanglement. Quantum entanglement is itself a soft and extraordinary thing. When two particles become entangled, they share a connection that persists regardless of distance. Measure one, and you instantly know something about the other, no matter how far apart they are. Einstein called this spooky action at a distance, and he was unsettled by it. But it is real. Experimenters have confirmed it again and again. Van Ramsdonk's insight was that in the holographic picture, the entanglement between regions of the boundary creates the connectivity of space in the interior. The more entangled two regions of the boundary are, the closer the corresponding regions of the interior seem. If you could cut the entanglement, if you could sever those invisible connections, space itself would tear. The geometry would fall apart. In other words, space is woven from entanglement. The fabric of the universe is stitched together by invisible threads of quantum connection. The world holds together because things are related to each other in ways we cannot see. There is something deeply beautiful about that. The universe is not just a collection of separate things moving through a pre-existing container. It is a web of relationships, and the web is the reality. Let your thoughts be a web like that. Light, connected, resting easily in the air. Nothing pulling too hard. Everything gently held. The idea that space emerges from entanglement has a name in the recent literature. Physicists call it ER equals EPR, which stands for Einstein-Rosen bridges and Einstein-Podolsky-Rosen pairs. Einstein-Rosen bridges are what we sometimes call wormholes, those hypothetical tunnels through space that connect distant regions. Einstein-Podolsky-Rosen pairs are entangled particles. The conjecture is that they are the same thing, that every entangled pair of particles is connected by a tiny wormhole, an infinitesimally small tunnel of space. This conjecture was proposed by Juan Maldacena and Leonard Susskind in 2013, and it has been at the heart of theoretical physics ever since. If it is true, then the deep structure of space is made of tiny wormholes, each one a manifestation of entanglement, each one a thread in the great fabric of reality. Close your eyes for a moment, if they are not already closed. Imagine the space between you and everything around you, the air, the walls, the world outside, not as empty distance, but as a web of invisible connections. Threads of relationship, finer than anything you could see, holding everything in a gentle, shimmering net. The night deepens. Outside, if you listen, or even if you do not, the world is quieter than it was. Sound travels differently in the late hours, softer, more willing to fade. Let us continue our wandering. One of the most wonderful things about the holographic principle is how it changes what we mean by inside and outside. In ordinary thinking, things are either inside a region or outside it. The inside has volume, depth, 3 dimensions. The outside has its own volume and depth. They are separate. But in holography, the inside and outside are more like different perspectives on the same painting. The inside of the universe, all the stars and galaxies and dark matter and dark energy, all the space through which light has traveled for billions of years, is equivalent to a description on the boundary. Inside and outside become translations of each other. Different views of the same fundamental truth. This is not unlike how a shadow is related to the object that casts it. The shadow is flat. It has only 2 dimensions, but it carries information about the 3-dimensional object that cast it. Move the object, and the shadow moves. Change the object, and the shadow changes. The shadow and the object are not the same thing, but they are telling the same story in different languages. Our universe in the holographic picture might be the shadow, rich, detailed, full of depth, but in a sense, the projection of something written on an unimaginably large surface at the boundary of everything. Feel how the darkness around you holds you, the way a shadow holds the shape of what cast it. Now, a question might arise softly in your mind. If the universe is a hologram, does that make it less real? Is there something sad or diminishing about this idea? And the answer, spoken gently, is no, not at all. Consider the music again. When you hear a piece of music that moves you, that opens something in your chest and makes you feel something you cannot name, it does not matter that the music is, at some level, just patterns of pressure in the air. The beauty is real. The feeling is real. The experience is real. The fact that it emerges from something more fundamental does not take anything away. It adds something. It adds a kind of wonder. The holographic universe is like that. If everything you see and touch and love is a projection of information on a distant surface, that does not make it less. It makes it more. It means that the universe is more ingenious, more intricate, more quietly miraculous than it appears. It means that behind every familiar thing, there is a deeper structure, a more fundamental song. And tonight, you are resting inside that song, breathing with it, being held by it. Physicists sometimes speak of the holographic principle as a constraint on how much information can exist in a region of space. This is called the Bekenstein bound, named again for Jacob Bekenstein, whose early work on black hole entropy first opened the door to all of this. The Bekenstein bound says that the maximum amount of information that can be contained in a region of space is proportional to the area of its boundary, not to its volume. This is a profound limit. It says that a larger volume does not necessarily hold more information. What matters is the surface. Double the surface area, and you can, in principle, double the information content. But you cannot keep adding information to the interior indefinitely, as if space were an infinitely expandable filing cabinet. The surface sets the limit. Think of it like this. The number of photographs that can be taken of a landscape is limited not by how large the landscape is, but by how many angles you can view it from. The surface, the set of all possible viewpoints, is what determines the information. If you find yourself wanting to return to this kind of quiet wondering, do remember to check our playlist. There are many of these stories waiting there for you, each one a soft door into a different corner of the universe. Let your eyelids rest heavily now, if they wish to. You can follow the words with your ears even when your eyes are closed. The words will still be here. One of the fascinating puzzles that the holographic principle helps address is the question of what happens at the very smallest scales of space and time. There is a length so tiny it is almost unthinkable, called the Planck length. It is about 10 to the power of negative 35 meters. That is smaller than an atom by a factor so enormous that the comparison loses meaning. At the Planck scale, physicists believe space and time as we know them break down entirely. They become something else, something grainy, something discrete, something that our current theories cannot quite describe. The holographic principle offers a hint at what that something else might be. If space emerges from entanglement on a boundary, then at the Planck scale, where space becomes undefined, what we would find is the boundary itself, the raw information, the pixels, if you like, from which the holographic image is built. Some physicists imagine these pixels as tiny units of area on the boundary of space, each carrying exactly one bit of information. One yes or no, one on or off. And from the pattern of all these tiny yeses and nos, from this enormous, quiet array of information, the three-dimensional universe that we inhabit emerges the way a face emerges from the dots of a pointillist painting when you step back far enough. Step back far enough from a Seurat painting, and a woman holding a parasol appears, standing beside a river on a summer afternoon. Move closer, and she dissolves into dots of color. Reality might be like that. Step back from the quantum graininess of the Planck scale, and there is space. There is time. There is you lying in the quiet dark, breathing softly. Let your body sink a little more with each breath. The weight of you, the gentle, real weight, pressing softly downward, held by whatever supports you. This is what gravity feels like from the inside. This is the universe being kind. We are wandering now through some of the most beautiful territory in all of physics, the connection between information, space, and the nature of what is real. And we are doing it the best way there is, slowly, without urgency, in the company of the dark. There is a thought experiment that physicists love to discuss in the context of holography. It is called the firewall paradox, and it was proposed in 2012 by a group of physicists known by the acronym AMPS for Almhiri, Marolf, Polchinski, and Sully. Their thought experiment concerns what would happen to someone falling into a black hole. In the old picture, Einstein's picture, a person falling into a large enough black hole would not immediately notice anything dramatic as they crossed the event horizon. Space would curve around them, gravity would pull, but there would be no wall, no barrier. The event horizon is not a physical surface. It is a mathematical boundary, the point beyond which return becomes impossible. An astronaut crossing it would feel nothing special in that moment. But AMPS argued that this picture cannot be complete because it conflicts with the holographic idea that information is preserved and lives on the horizon. If information is encoded on the horizon, they argued, then the horizon must have physical properties. It must be, in some sense, a real surface, and a real surface, when encountered at high speed, would feel like a wall of fire, a firewall. This created an apparent contradiction. Einstein says, the horizon is nothing special. Holography says, the horizon is everything. The paradox remains unresolved, and physicists continue to work at its edges with great care and curiosity. But the very existence of the paradox points to something important. The holographic principle is not just a metaphor, it has teeth. It makes predictions that conflict with other predictions, and resolving those conflicts pushes physics forward. There is something very human in that. Growth often comes from paradox, from the place where two true things seem to say opposite things. You sit with the contradiction, and eventually, not by force, but by patience, a deeper truth begins to emerge, like the slow emergence of morning, not forced, just coming. The question of what space and time really are, at the deepest level, is one of the great open questions of physics. We experience space and time as fundamental. They feel given, built into the nature of things. But more and more, physicists are coming to the view that space and time are not fundamental at all. They are emergent. They arise from something more basic, the way temperature arises from the movement of molecules, or the way wetness arises from water molecules arranging themselves in a certain way. Neither temperature nor wetness is a single molecule. They are properties that appear when many molecules come together in certain configurations. Space and time might be like that. They are not there at the most fundamental level. They emerge like a scent from a flower, from the underlying structure of quantum information. This view has a name in the physics community. It is called the emergence of space-time. And It is one of the most active and fruitful areas of research today. Groups of physicists all over the world, in Princeton, in Cambridge, in Santa Barbara, in Tokyo, in Cape Town, are working on understanding how space-time emerges from quantum entanglement. Each small breakthrough is another pixel becoming clear in the great painting. Feel how peaceful it is to let a great question simply rest beside you. You do not need to answer it. The physicists are working on it. You can just rest. We would love to hear what you think about these ideas. Even a simple hello in the comments lets us know you found your way here. This community of curious, quiet minds is one of the most lovely things we have. One of the ways physicists study the emergence of space-time is through a tool called tensor networks. A tensor network is a mathematical object, a kind of diagram made of nodes and connections, that can represent the entanglement structure of a quantum system. When you draw the right kind of tensor network and think about what geometry it implies, you find that space-time emerges from its structure. This is abstract, but the image it suggests is beautiful. Imagine a great branching tree of connections, each branch representing a quantum relationship, a thread of entanglement. The overall shape of the tree, the pattern of how things are connected, generates the geometry of space. Change the connections, and space changes its shape. Strengthen certain entanglements, and space becomes flatter. Weaken others, and space curves. It is as if space is a garden and entanglement is the soil. The garden grows in the shape that the soil allows. Breathe into that image for a moment. A garden of space, growing from invisible soil, and you resting somewhere inside it, held by the curvature, warmed by the light of a star that is doing the same thing it has done every night for 5 billion years. The physicist Netta Engelhart has done some of the most important recent work on black hole information and holography. In 2019, she and her collaborator Ahmed Almheri, along with others, found a way to calculate the entropy of Hawking radiation that resolves a long-standing puzzle about information in black holes. Their work uses a mathematical object called a quantum extremal surface, a kind of surface in space-time that minimizes a quantum-corrected version of area. What they found was that the entropy of the radiation from a black hole rises at first, as you would expect, and then, after a very long time, it begins to fall. This behavior, called the Page curve, is exactly what you would expect if information is preserved. The radiation carries the information out, slowly and quietly, over enormous stretches of time. This result suggested that information is not lost in black holes. It escapes, encoded in the radiation, in a form so scrambled that it would take resources greater than the observable universe to decode it. But it is there. The information persists. Nothing is truly lost. That is a comforting thought to carry into sleep. Nothing is truly lost. The universe keeps its accounts. The night is very deep now, the kind of deep where even thoughts become gentle, barely formed, drifting like seeds in still air. You're doing wonderfully. Just being here, breathing and listening, is exactly the right thing. Let us continue very softly. One of the most intriguing aspects of the holographic principle is what it implies about the experience of living inside a hologram. If the universe is holographic, if three-dimensional space emerges from a two-dimensional boundary, then what does that feel like from the inside? The answer perhaps surprisingly, is it feels exactly like this, exactly like what you are experiencing right now. The richness of 3 dimensions, the solidity of objects, the sensation of moving through space, the feeling of time passing. All of it is what the hologram feels like from the inside, and it feels completely real, because in every meaningful sense, it is completely real. This is one of the most important things to understand about holography. It does not say that the world is an illusion. It does not say that nothing is real. It says that reality has a deeper structure than it appears to, that what we experience as fundamental might be emergent, might be the bloom of something more basic. But the bloom is real, the flower is real, the fragrance is real, you are real. Everything you feel and love and care about is real. The holographic principle is not a reason to doubt reality. It is a reason to be astonished by it. Let that feeling of astonishment be quiet and warm, the way embers are warm, not burning, just glowing. There is a beautiful connection between holography and the nature of black holes that physicists sometimes call black hole complementarity. This is an idea developed by Susskind, 't Hooft, and others in the early 1990s. It says that a black hole looks different depending on who is observing it. For an observer falling into a black hole, nothing special happens at the horizon. They cross it smoothly and continue into the interior, unaware, at least for a time, that they have passed the point of no return. But for an observer watching from the outside, the person falling in never seems to cross the horizon at all. Due to the extreme warping of time near the event horizon, the infalling observer appears to slow down, to redden, to eventually fade away, just at the edge, but never to cross. The information about them seems to spread across the horizon, to sizzle there in the Hawking radiation, to slowly disperse into the outside universe. Both descriptions are true. Both observers are correct. There is no contradiction, because the two observers can never meet to compare notes. The information is not duplicated. It is complementary. Like two views of the same room from different windows, each complete and each different. This complementarity is not so different from everyday experience. The same event, a sunset, a conversation, a quiet evening, can look entirely different from different perspectives, and each perspective is true. Reality is large enough to hold all of them. You might want to add this to your sleep playlist. Many of our listeners return to these stories on nights when sleep is slow in coming. They tell us the stories work like a kind of anchor, something steady and slow to hold on to. The mathematics of holography has led to some remarkable insights into very different areas of physics. One of the most surprising is in the study of condensed matter physics, which is the study of materials, of solids and liquids, and the exotic states of matter in between. Things like superconductors, which conduct electricity without any resistance, or quantum spin liquids, which are strange phases of matter that have no conventional order. Physicists have found that the mathematics of holography, the ADS/CFT correspondence, can be used to calculate properties of these exotic materials in a way that other methods cannot. By translating the problem of strongly interacting electrons in a material into the problem of gravity in a higher dimensional space, physicists can extract results that would otherwise be out of reach. This is one of the most remarkable things about mathematics. A tool built to think about black holes and the nature of space-time can turn out to be perfectly suited to thinking about electrons in a copper wire. The universe does not compartmentalize its mathematical truths. They apply everywhere in ways we do not always expect. Feel how everything connects in the end. How the physics of the very large and the physics of the very small reach toward each other across the distance. How the universe is, in some sense, all one thing, expressing itself through the language of mathematics. Let your mind be quiet now. Let the thoughts thin out like mist. You do not need to hold any particular idea. Let them all drift past like clouds in the slow dark of early morning. In the holographic picture, something remarkable happens to the concept of locality. The idea that things that are close together in space should interact strongly, while things that are far apart should interact weakly. Locality is one of the foundations of physics. It is why you can close a door and feel safe from the weather outside. It is why signals take time to travel from one place to another. But in holography, locality in the interior of space is not fundamental. It emerges from the pattern of entanglement on the boundary. Two regions of the boundary that are highly entangled give rise to regions of the interior that are close together. Two regions that are barely entangled correspond to regions of the interior that are far apart. This means that the closeness of things, the nearness you feel to whatever is around you, is an emergent property. It is real, but it is built from something even more fundamental, the web of quantum relationships on the boundary. Lie quietly with that thought. The nearness of things is real. The warmth of what is close to you is real. But at the deepest level, closeness itself is a kind of relationship, a pattern in the entanglement of the world. And perhaps that is what closeness always has been, even before the physics told us so. We are past the midpoint of the night now, in that soft territory where dreams begin to stir at the edges of thought, where the boundary between waking and sleeping becomes as gentle and porous as fog. Let it be gentle. Let it be porous. The universe, we have been saying, may be written on its own surface. Let us think now about what that surface might be like. In the specific version of holography that Maldacena developed, the ADS/CFT correspondence, the boundary is a surface in a specific kind of geometry. Anti-de Sitter space has a boundary that is like the edge of a disk, infinitely far away in some sense, but present in the mathematics as a definite surface on which the dual theory lives. The boundary theory is a quantum field theory, a theory of fields and particles without gravity. And yet, it perfectly encodes the physics of gravity in the interior. When physicists work in this framework, they sometimes speak of the boundary as the lower level of reality and the interior as the higher level. Not higher in importance, they are equivalent, but higher in the sense of having more dimensions, more apparent complexity, more of the things we associate with the physical world. This language of levels is evocative. It suggests something like a building, each floor containing the same information as the one below, but arranged differently, appearing different, experiencing itself differently. And the people on each floor, if they were thoughtful enough, could work out the structure of the floor beneath, could understand that their rich, complex world was being generated by something simpler, something foundational. We are the people on the upper floor, and physicists are the thoughtful ones working out the structure below. Let your thoughts be like that, reaching gently downward, not with urgency, just with curiosity. What is beneath the surface of things? What holds it all? The holographic principle has a fascinating relationship with what physicists call degrees of freedom, which is a technical way of saying the number of independent ways a system can vary. A particle in free space has many degrees of freedom. It can move in any direction. It can spin. It can have various energies. A system of many particles has enormously many degrees of freedom. What the holographic principle tells us is that the degrees of freedom of a region of space are not proportional to its volume, as you might expect, but to the area of its boundary. This is a massive reduction. Imagine a room. Naively, you might think that the amount of information needed to describe everything in the room grows with the volume of the room. The more space, the more stuff, the more information. But holography says no. The amount of information is set by the area of the walls. The room could be as tall as a mountain, but its information content is set by its footprint. This is called the holographic bound, and it is one of the deepest things we know about the relationship between information and space. Think about your own room, or wherever you are right now, the walls, the ceiling, the floor. In some sense, in some deep and mathematical sense, all the information of what you experience is encoded on those surfaces, not in a mystical way, in a physical way, in the way that mathematics describes. The surfaces are enough. The surfaces contain everything: your ceiling, your walls, your quiet floor, holding the universe for you. A gentle prompt. If you are enjoying this journey, please do consider leaving a like. It takes one small moment and means a great deal to us. Thank you, truly. One of the most stunning things about the holographic principle is that it was discovered not by looking at the universe from the outside, which of course we cannot do, but by following the mathematics where it led. Physicists did not start by saying, "Let us find out if the universe is holographic." They started by asking, what happens to information in a black hole? What is the entropy of a horizon? How does gravity relate to quantum mechanics? And the answers led step by step to the holographic principle. This is how physics so often works. You follow a thread, not knowing where it goes, and it leads somewhere extraordinary, somewhere you never planned to arrive, somewhere that changes how you see everything. The history of physics is full of these accidental arrivals. Maxwell followed the mathematics of electric and magnetic fields and discovered that light was an electromagnetic wave. Einstein followed the principle of relativity and discovered the curvature of space-time. Dirac followed the mathematics of quantum mechanics and predicted the existence of antimatter. The mathematics knew, before the physicists did, what was true. There is something humbling and wonderful about this. The universe is more self-revealing than we give it credit for. Follow the clues carefully enough, with patience and without prejudice, and the universe tells you its secrets. Let that feel like permission to rest. You do not need to figure anything out tonight. The universe will keep revealing itself. It has been doing so for 14 billion years, and it shows no sign of stopping. The deepest hours of night have a quality of softness that is different from any other time. The world is wrapped in itself, turned inward breathing slowly. Let yourself be part of that inward breathing, part of the world at rest. We have been speaking about information, about how it might be encoded on surfaces, about how it gives rise to space and time and gravity. Now, let us speak about something even stranger and more beautiful. The idea that space itself might be made of error correction. Error-correcting codes are something that engineers invented to solve a very practical problem. When you send information through a noisy channel, through a telephone line, through the radio waves between a spacecraft and Earth, errors creep in, bits get flipped, the message gets corrupted. Error-correcting codes solve this by encoding the message in a redundant way, so that even if some bits are lost or flipped, the original message can be recovered. Your phone does this. Your internet connection does this. The radio signal from the Voyager spacecraft, now more than 20 billion kilometers away, does this. Error-correcting codes are everywhere in modern technology. But here is the remarkable thing. In 2015, a group of physicists, including Ahmed Almheri, Shidong, and Daniel Harlow, published a paper arguing that the holographic principle has the mathematical structure of an error-correcting code. The quantum information on the boundary encodes the physics in the interior in a redundant way, so that even if part of the boundary is removed or obscured, the interior physics can still be reconstructed from what remains. This is a deep and beautiful result. It means that the universe is, in some sense, robust. The information that makes up reality is not fragile. It is encoded redundantly so that it can survive partial loss. The universe has built-in error correction. Think about what that means. The fabric of space, the ground of reality, is resilient, not fragile, not easily broken, held in place by redundant, overlapping layers of information that support each other. The way a net is stronger than any single thread. You're held in that net. We all are. The universe does not drop its information. It holds it redundantly, carefully, with all the patience of mathematics. This idea connects to a concept called quantum error correction, which is also at the heart of the effort to build quantum computers. A quantum computer must protect its fragile quantum information from environmental noise, from the small disturbances that the world is constantly making. It does this using quantum error correcting codes. And those codes, it turns out, look mathematically very similar to the structure of holography. So, the same mathematics that might describe the deep structure of space-time is also being used in laboratories to protect the delicate quantum states that will one day power entirely new kinds of computers. The universe's architecture and the engineer's architecture speaking the same language. There is a playlist of all our sleepy science stories waiting for you, each one a little journey like this one. We will leave a link for you to find when you are awake and looking for your next bedtime companion. Let the mathematics rest now. Let it sit in the background like a piece of music playing in another room, present but not demanding attention, just there. The physicist Shinsei Ryu and Tadashi Takayanagi made a discovery in 2006 that has become one of the most celebrated results in the study of holography. They found a formula for entanglement entropy, the entropy that measures how quantum entangled a region of the boundary is with the rest of the boundary. And they showed that this entropy is equal to the area of a minimal surface in the interior of the holographic space. This is called the Ryu-Takayanagi formula. It is simple in form, extraordinary in meaning. It says, to find out how entangled a region of the boundary is, look at the interior and find the minimal surface that separates that region from the rest. The area of that surface, measured in Planck units, gives you the entanglement entropy. This formula links two apparently very different things: quantum entanglement on the boundary and geometry in the interior. Entanglement creates geometry. The more entanglement, the more space. The shape of space is the shape of entanglement. Ryu and Takayanagi found this formula by computation, by following the mathematics. But when they saw what it said, it must have felt like recognizing something, like catching a glimpse of a very deep truth through the mathematics. The way you sometimes catch a glimpse of understanding in a dream, the formula has been tested and extended and deepened in the years since. It has become a central tool in the study of holography, and it continues to point toward the same essential truth. Space-time is built from entanglement. Space is woven from invisible connections. The universe is a web of relationships, expressing itself as geometry. And you, lying in the dark, are part of that web, entangled in the quantum sense with everything around you. Part of the pattern that weaves space into being. The night holds you lightly, the way water holds a leaf that has fallen onto a still pond, without effort, without urgency, just holding, just floating, just being. We are deep in our wandering now. The ideas have settled around us like snowfall, soft, covering everything with a layer of quiet. Let us think for a moment about time. Time is perhaps the most mysterious dimension of all. Space we can move through in any direction, forward, backward, left, right, up, down. But time only flows one way, from past to future, from what was to what will be. We cannot go back. We can only move forward, one moment at a time, like a slow river that knows only one direction. The question of why time flows, why there is a past and a future, why the universe has a direction, is called the problem of the arrow of time. And it is one of the deepest puzzles in physics. Because the fundamental equations of physics, the laws of motion, the laws of quantum mechanics, work equally well in both directions of time. There is nothing in the fundamental laws that says time must flow forward. And yet, it does. The answer most physicists favor has to do with entropy, with disorder. The past had low entropy. The early universe was in a very special, very ordered state. And since then, entropy has been increasing. The universe has been becoming more disordered, more spread out, more mixed. And this increase in entropy is what we experience as the passage of time. The arrow of time is the arrow of increasing entropy. But in the holographic picture, time takes on a new aspect. Because if the interior of space emerges from the boundary, then time in the interior must also, in some sense, emerge from the boundary. The experience of moments unfolding, of causes preceding effects, of the past being fixed and the future being open, all of this might be emergent from the quantum dynamics on the boundary. There is something very peaceful about that. The flow of time, that most intimate and personal of experiences, might be a bloom, an emergence, a beautiful consequence of deeper mathematical relationships. Not an imposition, not a prison, just the way that quantum entanglement looks when viewed from the inside. let your sense of time soften now. Let the urgency of the clock fade. There is no schedule in the deep hours. There is only the slow, unhurried flow of one moment into the next. There is a physicist named Brian Swingle who has done beautiful work on the connection between entanglement and space-time. Swingle studied something called the multi-scale entanglement renormalization, ansatz, a mathematical structure for describing how quantum systems are organized across different scales. And he noticed that this structure, which is called mirror for short, looks geometrically like a slice of anti-de Sitter space. In other words, the mathematical structure that physicists use to describe entanglement in a quantum system organized across scales generates a geometry that looks like hyperbolic space. The geometry of space emerges from the structure of entanglement, even in a concrete and visual mathematical sense. This is the kind of discovery that makes physicists feel they are on the right track, not because it proves everything, but because it makes the pieces fit together in a new way, like finding the right shape of puzzle piece, not because you forced it in, but because it simply fits, because it was always the right shape, waiting to be found. We are so glad you are here with us tonight. If these wanderings have given you something, a little peace, a little wonder, a little company in the quiet hours, please do consider subscribing to the channel. More of these stories are waiting for you. Let us think now about the cosmic microwave background, the faint glow of radiation that fills the universe in every direction. This radiation is the afterglow of the Big Bang, the echo of the moment when the universe first became transparent to light, about 380,000 years after it began. The cosmic microwave background is incredibly uniform, almost perfectly the same temperature in every direction, about 2.7 degrees above absolute zero, but not perfectly uniform. There are tiny variations, tiny fluctuations in temperature at the level of a few parts in 100,000. These tiny fluctuations were imprinted on the early universe by quantum fluctuations, by the inherent uncertainty of quantum mechanics amplified to cosmic scales during a period of rapid expansion called inflation. They are, in a very literal sense, quantum writing on the sky. The universe left its quantum fingerprints in the light that has been traveling ever since. The holographic principle might have something to say about these fluctuations. Some physicists are exploring whether the statistical patterns of these temperature variations might be consistent with a holographic origin, whether the universe we inhabit might have begun as a hologram, with the three-dimensional Big Bang emerging from a lower dimensional boundary. This is speculative. It is frontier research at the very edge of what is known. But the edge of what is known is a very good place to look for the next beautiful thing. The universe is enormous, and it has been patient with us. 14 billion years of existence, and only in the last few centuries have any of its inhabitants managed to work out even a fraction of its structure. We are very new here, and the universe is still revealing itself to us slowly with the patience of something that has all the time in the world. Feel that patience settling over you. The universe has been here for 14 billion years. It will be here tomorrow. There is no rush. Let your breath be your anchor now. Everything else can drift. Thoughts, images, fragments of the ideas we have been walking through, but your breath is steady, in and out, the simplest rhythm in the world. We are approaching the end of our wandering, but gently, unhurried, like a river approaching the sea. One of the most intriguing applications of holographic ideas is to the study of quantum gravity, the as-yet undiscovered theory that will reconcile quantum mechanics with Einstein's general relativity. These two theories, taken separately, are among the most successful in the history of science. Quantum mechanics describes the very small with extraordinary precision. General relativity describes the large, planets, stars, galaxies, the universe itself, with extraordinary precision. But they are deeply incompatible at the mathematical level. When you try to combine them, infinities appear, nonsensical results emerge, and the mathematics breaks down. A theory of quantum gravity would unify them. It would describe what happens at the Planck scale, at the smallest and densest possible scales of space and time, where both quantum effects and gravitational effects are important. And holography suggests that a theory of quantum gravity in the interior of space is equivalent to a non-gravitational quantum theory on the boundary. If you understand the boundary theory, you understand quantum gravity. This is the promise that keeps many physicists working long into the night. Not because the answer will be found soon. It may take decades, or lifetimes, or generations, but because the direction is clear, because the path, if not fully mapped, is at least indicated, because there is a light at the end of the long tunnel of equations, and it is the light of understanding. And somewhere in laboratories and universities and offices all over the world, people are working toward that light, quietly, carefully, with patience and joy, doing the thing they love most, which is thinking hard about the nature of reality. What a beautiful thing to do with a life. Let your own thoughts about what you love, what you care about, what you find beautiful, let them drift through you now, very gently, not as things to hold, just as things to notice, small lights in the dark. The holographic principle has deep connections to something called quantum chaos, the study of how quantum systems that are classically chaotic behave. Chaos, in the classical sense, is when tiny differences in initial conditions lead to wildly different outcomes. The famous butterfly effect. Quantum systems do something similar, but in their own quantum way. Holographic systems, those described by the ADS/CFT correspondence, are maximally chaotic in a precise sense. They scramble information as fast as any quantum system possibly can. Information that falls into a holographic system is distributed across all the degrees of freedom of the boundary as quickly as possible, in a process called quantum information scrambling. Black holes are also thought to be maximal scramblers. Information that falls into a black hole is distributed across its horizon, its entire surface, almost instantaneously. The horizon is the fastest possible scrambler of information. And in the holographic picture, the horizon and the boundary are related. The scrambling of the black hole is the scrambling of the holographic system. This connection between black holes, holography, and quantum chaos is one of the most active frontiers in current physics. Researchers like Patrick Hayden, John Preskill, and Alexei Kitaev have all contributed beautiful ideas to this field. Kitaev, in particular, introduced a simple model called the Sachdevye-Kitaev model, or SYK, which captures the maximal chaos of black holes in a framework simple enough to study mathematically. It has become one of the most studied models in theoretical physics in recent years. You do not need to remember the names or the models. Just let the feeling of it rest with you. There is a web of connections between black holes, between quantum systems, between information and geometry that physicists are slowly mapping. And the map is beautiful. If you are drifting now, that is perfectly right. Let the words become softer, more like weather than content. Just something happening around you, gentle and continuous. There is a concept in holography called bulk reconstruction. The problem of figuring out what is happening in the interior of space, the bulk, given only the boundary data. This is a deep problem because the bulk has more dimensions than the boundary, and reconstructing extra dimensions from fewer dimensions requires careful and intricate mathematics. But physicists have made remarkable progress on this problem. They have developed methods for reconstructing bulk operators, quantum operations in the interior, from boundary data. And these methods reveal something striking. A single operator in the bulk can be reconstructed from many different regions of the boundary. The information about what is happening deep in the interior is spread across the boundary, encoded redundantly in overlapping regions. This redundancy is exactly the redundancy of an error-correcting code, and it explains something that had puzzled physicists. Why a local observer in the bulk, someone in the interior of space, can interact with local things in their neighborhood, even though, from the boundary perspective, that locality is not fundamental. The redundancy of the encoding is what makes local experience possible. The error-correcting structure of holography is what allows the interior to feel normal and local to its inhabitants. It allows it to feel like home, and the universe is home. This strange, deep, possibly holographic universe, it is the only one we know, and it is ours. We live inside it, not outside looking in. We are the interior, looking out at ourselves through the only instruments we have: our eyes, our minds, our mathematics. You're so close to sleep now. The ideas have softened into something more like texture than content, like the texture of a warm room, or the texture of a dream just beginning to form at the edges of thought. Let us keep going, very gently. One of the questions that naturally arises when thinking about the holographic principle is this: if our universe is a hologram, then where is the boundary? Where is the surface on which all this information is encoded? In the specific mathematical model of anti-de Sitter space, the boundary is well defined. It is a surface at infinity, at the very edge of space, where the conformal field theory lives. But our universe is not anti-de Sitter space. Our universe appears to be flat or slightly positively curved, and it is expanding. The boundary, if there is one, is not as clearly defined. Some physicists think the boundary of our universe might be related to its past or future, to the beginning of time, or to the far future, when the universe has expanded so much that space becomes effectively empty. Others think the boundary might be related to horizons, not event horizons of black holes, but the cosmological horizon that surrounds each observer in an expanding universe, beyond which light from distant regions has not yet had time to reach us. This is an area of active and lively research. The precise form of holography that applies to our expanding universe, if holography applies at all is not yet known. But the evidence that it should apply, from the Bekenstein bound, from the Ryu-Takayanagi formula, from the connections between entanglement and space-time, is mounting. The universe, it seems, is trying to tell us something, and we are very slowly learning to listen. Let the not knowing be soft. The universe has been full of unknowns for 14 billion years, and it has been fine. It will be fine a little longer. There is a beautiful metaphor that the physicist Lee Smolin has used to describe the holographic principle. He compares it to an old-fashioned telegraph system where messages are encoded as sequences of dots and dashes on a one-dimensional line, a wire, and decoded at the other end into complex three-dimensional reality. The message is flat. The world it describes is rich and full. Smolin notes that we are always, in some sense, perceiving the universe through a boundary. Our eyes receive light, two-dimensional patterns of photons on our retinas, and our brains reconstruct from that flat information a rich, three-dimensional world. The reconstruction is so seamless, so immediate, so automatic, that we never notice the flatness of the input. We only experience the depth of the output. The holographic principle suggests that the universe itself might work this way. The boundary carries the information. The interior is the reconstruction. And the reconstruction is so seamless, so immediate, so deeply embedded in the nature of things, that from the inside it is indistinguishable from a fundamental reality. You are the reconstruction, experiencing itself as the original, and somehow that is not less. It is more. We are so grateful for every person who finds their way to this channel. If you want to support this work, the simplest thing you can do is share these stories with someone you know who might benefit from a little quiet wonder at the end of the day. Let us think now about one of the pioneers of information theory, Claude Shannon, who in 1948 published a paper that changed the world. Shannon was working at Bell Labs, thinking about the problem of communication, how to send messages efficiently and reliably over noisy channels. He invented a rigorous mathematical theory of information, defining a quantity called entropy that measures the amount of uncertainty or information in a message. Shannon's entropy, his measure of information, looks mathematically identical to the entropy that appears in thermodynamics, the entropy that grows with time, the entropy of the Bekenstein bound. This is not a coincidence. Information and entropy are the same thing, viewed from different angles. One is the uncertainty of a message. The other is the uncertainty of a physical system. They are the same mathematical beast. When physicists speak of the information encoded on the boundary of the universe, they are using Shannon's ideas. They are speaking of a fundamental currency of the universe. Not matter, not energy, but information. The ability to answer yes or no questions about the state of things. And the universe, it seems, is very careful about this currency. It does not create it or destroy it. It only rearranges it, encodes it, scrambles it, and, according to the holographic principle, writes it on its own surface. The most fundamental thing in the universe may be information, and information, by its nature, is relational. It is always information about something. It is always a question with an answer, a signal with a receiver, a pattern that means something to something else. The universe is, at its deepest level, relational. It is made of relationships. and relationships, by definition, require connection. Everything is connected to everything else in the deep structure, not as a comforting platitude, but as a mathematical fact. We are in the last long reaches of the night now. The stars outside, if you could see them, are the same stars that have watched over every sleeping person who has ever lived. There is something very quiet about that. The holographic principle connects to a deep question about the nature of observers. In quantum mechanics, the act of observation plays a strange role. Before observation, a quantum system exists in a superposition of states, all possible outcomes hovering together, unresolved. After observation, one outcome occurs. The wave function collapses, as physicists say. But who is the observer? What counts as an observation? This is the measurement problem, and it is one of the deepest unresolved issues in the foundations of quantum mechanics. Different interpretations of quantum mechanics answer it differently. The Copenhagen interpretation says the observer is anything classical that interacts with the quantum system. The many worlds interpretation says there is no collapse. All outcomes occur in branching worlds. Other interpretations have other answers. In the holographic picture, there is a natural role for the observer. The boundary theory is the fundamental description. Events in the interior, the three-dimensional world, are observable from the boundary. And the act of observation in this framework is connected to the entanglement structure of the boundary. The observer and the observed are not separate in holography. They are part of the same entangled system. The observation is built into the structure of reality. This is a gentle thought to carry into sleep. You are not separate from the universe you observe. You are part of it. Your presence, your observation, your very existence is woven into the fabric of the entangled whole. The boundary does not observe the interior from outside. The boundary is the interior, seen differently, and you are part of both. Let your sense of separation soften now. The edges between you and the world, between inside and outside, between observer and observed, let them become as gentle and permeable as mist. There is a physicist named Raphael Bousso who has made important contributions to holography. In 1999, he formulated a general version of the holographic bound, a version that applies to any space-time, not just specific mathematical models. He called it the covariant entropy bound. It says that the entropy of matter crossing any light sheet, a surface traced out by light rays, cannot exceed the area of the light sheet in Planck units. This is a general principle believed to hold in any consistent theory of physics. It constrains how much information can exist in any region of the universe in a way that depends only on geometry and the speed of light. It is, in a sense, a law of nature about information, a fundamental rule built into the structure of space-time. Bousso's work helped transform holography from a specific mathematical trick into something more universal. It suggested that holography is not just a feature of certain mathematical toy universes. It is a deep truth about how information and space are related everywhere and always. Let that universality be comforting. The rules of the universe are the same everywhere. In the farthest galaxy, around the light of the most distant star, the laws of information hold. The holographic principle holds. The same quiet mathematics that governs the space around you governs space without limit. One universe, one set of laws. written everywhere in the same gentle language. We are so grateful you have stayed with us this far. If you have been finding this journey soothing, please do leave a comment, even a word or two. It truly means the world to us and helps these stories find more quiet minds who need them. There is something called the principle of unitarity that underlies all of quantum mechanics. Unitarity says that quantum evolution, the way quantum states change over time, is reversible. No information is ever truly lost. The state of a quantum system today completely determines its state in the future, and vice versa. You could, in principle, run the evolution backward and recover the past from the present. This principle is what makes the black hole information paradox so sharp. If information is lost in a black hole, if the quantum evolution is not unitary, then one of the foundational principles of quantum mechanics is violated. This is why physicists take the paradox so seriously. Not because black holes are immediately relevant to everyday life, but because the resolution of the paradox will tell us something deep about the foundations of physics. And the holographic principle, as we have seen, suggests that information is not lost, that the entropy of Hawking radiation follows the page curve, that the boundary description, which is unitary by definition, implies that the interior description must also be unitary, even when it does not appear so from the interior perspective. This is one of the most satisfying things about holography. It provides a home for unitarity. It says that even when things look like they might be going wrong, when information seems like it might be disappearing into the darkness, there is a larger description in which everything is fine, everything is preserved, everything is connected and accounted for. From the larger perspective, nothing is lost. From the larger perspective, you are always held. The words are becoming softer now, like music played in a distant room. Let them be that way. Let them wash over you without trying to catch each one. We have been speaking about very large ideas, about the nature of space and time, about information and entanglement, about the deep structure of reality. Let us come a little closer to home now. Let us think about light. Light is perhaps the most wonderful thing in the universe. It is both particle and wave. It travels at the same speed for every observer, no matter how fast the observer is moving, a fact that Einstein found so extraordinary that it became the foundation of his entire theory of relativity. Light carries energy. Light carries information. Light is how we see the universe. And in the holographic picture, light plays a special role. The boundary of anti-de Sitter space is where light travels. It is the conformal boundary, which means it is defined by the paths of light rays. The boundary is, in a sense, made of light. And the theory that lives on the boundary is a conformal field theory, a theory that respects the symmetries of light, the symmetries that leave the physics unchanged when you rescale distances and times. Light is at the boundary of things. Light is at the edge where the holographic encoding happens. Light is the language in which the universe writes its information. And when light reaches your eyes, when the faint glow of the night finds its way through your eyelids, it is bringing information from the boundary of things to the center, from the edge of the hologram to the interior, from the surface to the depth. Even the softest light is a messenger. Let the darkness be full of soft messengers, carrying their quiet information. The idea that the universe might be informational might be made at the deepest level of something like computation, connects with a long tradition of thought in physics and mathematics. The mathematician John von Neumann, who was one of the founders of both modern computing and quantum mechanics, saw deep connections between entropy and computation. Shannon formalized information theory in a way that von Neumann recognized immediately as related to his own work in quantum mechanics. Later, Rolf Landauer showed that the physical erasure of information, actually deleting a bit, must always produce heat. There is a physical cost to forgetting. The universe does not allow free forgetting. Every bit erased must pay the thermodynamic toll. This result, known as Landauer's principle, was long considered somewhat theoretical. But in recent years, experiments have confirmed it with increasing precision. Forgetting has a physical price. Information and physics are not separable. The universe is not indifferent to whether its information is kept or discarded. The universe, in other words, remembers. Everything that has ever happened is still encoded somewhere in the quantum state of the universe, scrambled but present. The past is not gone. It is folded into the present, compressed into entanglement, waiting, in principle, to be read. Your own past is still there, in some sense. Every moment you have lived is still encoded in the universe's quantum state. Not accessible, not recoverable in any practical sense, but present. Part of the vast, entangled record of everything that has ever been. You are the living present of a universe that still holds all its past. And what a rich past it has had. Let your own memories drift gently now, not as things to analyze, just as soft light illuminating the room of you. There is a beautiful phenomenon in quantum mechanics called quantum teleportation. It is not the teleportation of science fiction. You cannot beam yourself across a room. But information can be transferred from one place to another using entanglement and classical communication in a way that is genuinely extraordinary. The quantum state of a particle can be perfectly transferred to another particle in a distant location without the original particle physically moving there. Quantum teleportation has been demonstrated experimentally across distances of hundreds of kilometers, through fiber optic cables, through free space, between satellites and Earth. The entanglement does the work. The connection does the work. The relationship between particles is powerful enough to carry the full information of a quantum state across any distance. In the holographic picture, quantum teleportation plays a role in understanding how information gets from the interior of a black hole to the outside, how the information encoded in Hawking radiation can carry the full content of what fell in. It involves a kind of quantum teleportation through the entanglement between the interior and the exterior. The interior and exterior of a black hole are connected by entanglement, and through that entanglement, information flows slowly over vast spans of time from one side to the other. The universe is constantly teleporting information through its quantum connections. Everything is in conversation with everything else through the invisible language of entanglement across any distance. The night is beginning to thin at its very edges. Not visibly, but you can feel it perhaps, that subtle shift in the quality of darkness that comes before any light appears, the night being aware of the approaching morning, We are near the end of our wandering now, but close your eyes a little more firmly if you like. Stay here with us a while longer. The morning can wait. We have been speaking about the holographic principle in the context of physics, in the mathematical framework of string theory and quantum gravity. But the idea resonates in other places too. The philosopher David Chalmers has written about what he calls the simulation hypothesis, the idea that our universe might be a kind of simulation running on some physical substrate external to itself. This is a philosophical, not a physics, position. But it rhymes with holography in an interesting way. In both cases, the question is, what is the relationship between the experience of reality and its underlying substrate? What is the reality behind the reality? Chalmers does not argue that the simulation hypothesis makes our experience less real. He argues the opposite. If we are in a simulation, the simulation is real. Its laws are real. The experiences it produces are real. The deeper substrate does not diminish the reality of the experience. It is simply a different level of description. This is the same move that holography makes in physics. The boundary description is not more real than the bulk description. The bulk is not an illusion. Both descriptions are real, and they are equivalent. The levels of description are different, not ranked. Reality does not have a true level. It has many levels, each real, each valid, each complete in itself. The level at which you experience the world, with its colors and textures and sounds and feelings and relationships and meanings, is a real level. It is as real as the boundary theory. It is as real as the quantum entanglement. It is as real as anything can be. And it is the level at which love happens, and kindness, and wonder. The level at which you lie awake in the quiet dark, listening to a voice speak softly about the nature of the universe. That is the level that matters to you, and it is real. Let that be the last firm thought you have tonight. The level of your experience is real. The world you know is real. And underneath it, holding it all, is something deeper and more beautiful than you can fully see. Something patient and mathematical and entangled and holographic, holding everything together in its invisible web. You do not need to understand it to rest in it. There is a physicist named Chiara Nappi who once described the feeling of working on fundamental physics as being like trying to read a message that is written in a language you're still learning. You can see that the message is there. You can make out some of the characters. You understand a phrase here and a word there, but the full meaning is still just beyond reach. That is where physics is right now with the holographic principle. Some of the characters are clear. Some of the phrases make sense. The broad outlines of the message are beginning to emerge, but the full text is not yet readable. Not yet. Perhaps not for a long time. And that is as it should be. The universe is not a crossword puzzle to be solved on a single afternoon. It is a mystery to be lived with, wondered at, approached with patience and humility and joy. The not knowing is not a failure. It is an invitation to keep looking, to keep wondering, to keep following the thread of curiosity wherever it leads. Tonight, it has led here, to this quiet hour, to this soft conversation about the nature of things, and that is a good place to have arrived. If you have enjoyed this journey, and we hope you have, Please do share these stories with anyone in your life who loves to wonder or who needs help finding sleep. And check our playlist. There are many more of these wanderings waiting for you there. The very last part of any night is its own kind of world. Time has slowed almost to stillness. The dark is full of a particular quality, peaceful and private and deeply kind. Let your breathing find its slowest, most comfortable rhythm now, the one that comes just before sleep, the one your body has always known. We have traveled together through some of the deepest ideas in physics, through the birth of the holographic principle in the entropy of black holes, through Maldacena's extraordinary discovery of the duality between gravity and quantum fields, through the emergence of space-time from entanglement, through the error-correcting structure of holography, through the arrow of time, through the scrambling of information and the persistence of the past. We have found at every turn that the universe is more connected than it appears, more coherent, more deeply organized. What looks like separation, the distance between things, the boundary between interior and exterior, is revealed to be something else: relationship, encoding, the translation of one description into another. The universe does not have unrelated parts. It has one great entangled whole, expressing itself through the beautiful illusion of separateness, so that things can relate to each other, so that there can be inside and outside, near and far, self and other. The separateness is real. The relatedness beneath it is also real. Both are true. And the truth of both is what makes the universe beautiful. Let your sense of yourself rest gently now. The boundary between you and the world, between your breath and the air, between your warmth and the warmth of wherever you rest, let it be soft. Not gone, just soft, just permeable enough to let the universe in. The stars that are outside right now, wheeling slowly on their ancient paths, are made of the same things you're made of: hydrogen and carbon and oxygen and iron and time. They were made in the first seconds of the universe, or in the bellies of long-dead stars that scattered their material into the cloud that became our solar system. You are made of stardust genuinely, not as a metaphor, but as a fact of chemistry. And in the holographic picture, you are also made of information, as is every star, as is every breath of wind, as is every moment of this night. All of it, information, encoded on a boundary we cannot see, projecting itself into the three-dimensional richness of experience. What a way to be! What a way to exist as information that has learned to dream. Because that is what you are, in a way. You are information complex enough to have experiences, complex enough to wonder about itself, complex enough to lie in the dark and listen to someone talk about the holographic principle and feel something: curiosity or peace, or a kind of wordless recognition. The universe has organized itself into something that can wonder about its own organization. That is not a small thing. That is perhaps the most remarkable thing. Be still now. Be here. In the quiet, in the dark, in the soft and unremarkable miracle of being a thinking, feeling arrangement of information inside a possibly holographic universe. There is nothing you need to do. There is nowhere you need to be. The universe is holding you, as it always has been, as it always will be. Its invisible web of entanglement runs through you and around you and between you and everything else. You are not alone in it. You could not be alone in it, even if you tried. The boundary, wherever it is, whatever it is encoding you right now. Your every breath, your every heartbeat, your every quiet thought is part of the information of the universe, written somewhere in the deep structure of things. Let that be a comfort. You are not separate from the universe. You are an expression of it. A particular, unrepeatable expression. This exact arrangement of atoms and thoughts and feelings and memories here in this moment, breathing this particular breath. And the universe is glad of it, not in a sentimental way, in the way that a mathematical structure is glad of its own elegance, in the way that light is glad to travel, in the way that entanglement is glad to connect. The universe is glad in its own deep and wordless way that you are here. Let your eyes be closed. Let your jaw be soft. Let your hands be open, relaxed, resting. The holographic principle says that the interior is encoded on the boundary, that what is deep is written on the surface, that inside and outside are different descriptions of the same truth. And perhaps there is something like that in you too. Perhaps the deep truth of what you are, what you have experienced, what you have felt, what you have loved, is encoded on some surface that is simpler than the full complexity of your inner life. Perhaps you are, in your own way, a hologram, rich and deep and three-dimensional in experience, but fundamentally relational, fundamentally connected, fundamentally made of the relationships you have with others and with the world. You are made of connection, and so is everything else. Sleep now, if you're ready, or rest in this quiet place for a while longer. There is no hurry. The night is large enough to hold whatever you need. The universe is still out there, doing what it has always done. The galaxies are slowly turning. The black holes are glowing with their faint, Hawking radiation. The quantum fields are vibrating. The entanglement is holding space together. And you are here, a small and extraordinary knot of information in the great web, warm, breathing, resting. That is more than enough. That is everything. Close your eyes. Let the words become a gentle sound like rain on a window or wind in trees, and let the holographic universe hold you as you sleep. We will be here again next time, whenever you need us, with more quiet stories about the beautiful, strange, deeply connected world you live in. Good night. Rest well.